we have a fixed end and also horizontal spring. Because this is horizontal spring, so if we assume the distance at the top point is equal to delta, and then the reaction force is equal to the spring of the stiffness of the spring times the delta. But you have to give the correct direction of the reaction force. Because you assume the elongation in the left direction, right? So the restoring force must be in the right direction. Can you understand? Because you assume the elongation in the left direction, if you have a tension to the spring, of course, the reaction force also in the tension direction. So this is a rightward direction reaction force. So here we cannot take a moment for point A because we don't know the moment for section A. A is a fixed end, so you have to make a judgment on the direction based on the assumption of the displacement of the spring. In this case, we assume the displacement in the leftward direction for the spring. So the reaction force must be in the opposite direction, the rightward direction. Again, we assume the positive response, and this is the equation I provide you. The equation I provide you is that we cut off any cross section. And then the moment due to this rotor force is equal to the force times the distance between B and this point. The distance between B and this point is equal to delta plus y. But please understand, delta must be positive. It is not ordinate. If this is negative plus y is not equal to the total distance. So total distance is equal to positive delta plus y. For the reaction force, it is equal to the reaction force times the distance L minus x. So the rotor force produces hogging moment. So rotor force produces hogging moment, so this is negative, and the reaction force produces sagging moment, so this is positive. So this is positive and this is negative. So this is the equation we obtained. So the right side term looks complicated, but don't worry about that. You just need to obtain the particular solution, which is equal to the right side terms divided the coefficient before y, so we can obtain the solution. And how about the boundary condition? Rotation here is equal to 0, deflection here is equal to 0, but deflection at point B is not equal to 0. Please understand, deflection at point B is equal to YB. YB means the deflection at the point B. The deflection at the point B is negative, so it is equal to negative delta. So here YL is equal to negative delta. So here's a negative delta, and after obtaining the boundary condition, it is easy to obtain the determinant, and also, and the solution is not so easy. I can show you. So this is characteristic equation finally we obtained. And if we use a numerical method, it is easy to obtain the solution, but only when the very specific value about x is given. X represents the stiffness of the spring. So when x is given, it's easy to obtain the solution for this equation, because you can plot two curves, and the intersection point is just a solution. Here I provide you the general solution for different a's. So here we introduce a parameter eta, and eta satisfies this equation. When eta satisfies this equation, you can obtain the solution about mu. And the mu is obtained between the eta and the mu. So for different s value, we can obtain the corresponding eta. So eta is a function about x. Arrow is given, EI is given. So when S is given, we can obtain the eta value. So after obtaining the eta value, we can obtain the corresponding mu value. Mu value. And this mu value is obtained from this equation based on the numeric solution. So here I provide you as a numeric solution for different eta and the corresponding solution about mu. Okay, and this is a final solution about the critical load. So this is a standard formula, and the mu represents the effective length of the column, because mu times arrow represents the effective length in the design for the steel column or steel columns. Okay, so here, and we have two special cases. When eta is equal to 0 means AC is equal to 0. So when the spring stiffness is equal to 0, spring stiffness equal to 0, that means that there is no spring. So this is a free end at the top. Okay, so when AC is equal to 0, it is corresponding to the case given here. It's corresponding to the case given here, right? Okay, the spring is equal to 0 means no springs, right? So in this case, mu is equal to 2. And also here, from solution given here, also we obtain as a solution when eta is equal to 0, mu is equal to 2. So the solution is same as before. And how about the case when eta is equal to infinite? When eta is equal to infinite, the spring is same as a support, a horizontal support, okay? No movement. So this is corresponding to the case given here. So this is corresponding to this case. It's corresponding to this case. Okay, it's corresponding to this case. The stiffness of the spring is infinite. So this is like a rigid support. Okay, so in this case, mu is equal to 0.7. So here, mu is equal to 0.7. Okay, and for general case, the stiffness is between 0 and infinite. Okay, so when we have a different S value, we can obtain the corresponding eta, and then from this table we can obtain the mu value. Okay, so this is a solution, and also the solution obtained from this example can be applied to obtain the critical load for these two structures. Okay, in the first structure we have elastic bar here. So this is an elastic bar, but this bar is not subject to compression axial force. So this bar has no stability problem. So the inference of this bar is just equivalent stiffness. So the equivalent stiffness is obtained from this formula. So when EA is provided, when arrow is provided, ACE is also provided. So based on the obtained ACE, you can calculate the corresponding value of the eta, and based on the given eta, we can obtain the mu value. So from this equation, we can obtain the critical load. Okay, and similarly, in this case we have a second column here, but this column is not subject to axial force, so there is no stability problem for this column, and the effect of this column actually is equivalent stiffness. So this is the formula to obtain the equivalent stiffness. So after obtaining the equivalent stiffness, the equivalent system is same as the previous example. So we can get the solution from the previous table. Okay, and this is the final example. Okay, in this final example, I provide you two segments, and both are fractal structure. Okay, both are fractal structural components. So in this case, because as a moment, for the two segments will be different. I will show the expansion will be different. So you have to write down the governing equation segment by segment. Okay, when one segment is rigid, you just need to write down the equation for the fractal segment. But here, two segments, both fractal, so you have to write down two equations. Okay, I already show you how to obtain the reaction force at the point C. Okay, based on the moment about point C, and then we have a Y1 and a Y2. Okay, for segment, for any cross section within the low segment, the moment is equal to the moment due to the horizontal force and times and this moment due to the horizontal force, we cut off here and take the free body above this section as a free body. So we have two moment contributions. One is from the vertical force, the other one is from the horizontal force. So here we have two terms. Okay, but when x is between arrow and the two arrow, when x is here, okay, when x is here, we cut off this section, and again we take the segment above this section as a free body. In that case, we just have one force. Okay, we just have one force. So here we only have one term. Okay, so this is difference. This is a difference. Okay, and also please understand. Again, here's a delta plus y2, not delta minus y2. Actually, the moment due to the vertical force for the second segment for this section, okay, the moment due to this force is equal to distance from here to here, from this horizontal distance. So this horizontal distance actually is equal to the total distance minus the distance, minus this distance. So in principle, this is a difference. But why I still use plus? We didn't use minus. Didn't use difference. We still use delta plus y2, because for the second segment, so y2 automatically becomes negative value. Okay, y2 is the ordinate for the second segment. y2 here, y2 for this segment is a negative value. So delta is always positive. So delta plus y2 is same as positive value minus one value. Okay, because this is negative. So here we still use the same expansion for the first term. So this is a mathematics. For mathematics problem, you don't need to mind the real direction. You just need to assume, okay, it is a positive direction, and then the distance is equal to delta plus y. So when y is a positive value, this is a total distance. Okay, when y is a negative value, this means the difference. Okay, so you don't need to add the negative sign here again. So this term is same as this term. So only difference is that we don't have a horizontal force for the second segment. Okay, so we obtain two equations, and also you can obtain the solution for two equations. So this is the first equation, this is the second equation. This equation is obtained from the first equation after substitute HC value. HC value is based on the moment equilibrium. We already obtained this expansion. So we have two equations. So for two equations, you just need to obtain the corresponding solutions. We have two response solutions. Okay, so we have two solutions. So here we have obtained two solutions. And then, okay, the problem is that, okay, so totally we have how many unknowns? We have 5 unknowns, right? We don't know A1, B1, A2, B2, and delta. So we have 5. We have 5 unknowns. Okay, we have 5 unknowns. And so if you use the determinant, the matrix becomes 5 by 5. It is very difficult. It's almost impossible to obtain determinant. So here I do not recommend. So how to establish 1, 2, 3, 4, 5 boundary conditions? Not just 5 conditions. We still have the compatibility equation. Compatibility equation means for the intersection point. For example, this is an intersection point between the first segment and the second segment. From the first segment, we can obtain the deflection here, and also we can obtain the rotation here, right? And from the second segment, we are also able to obtain the deflection in the segment. But at the same point, the deflection and the rotation from the first segment should be same as the corresponding value from the second segment. So we can obtain the compatibility equation. Okay, so this is y1. okay, y1 equal, when y1 for the first segment, x equal to 0, it is equal to 0. This is a pin end. And at the internal support location, y1 is equal to 0, and also y2 is equal to 0. Okay, at the same point, because point C is an intersection point. The point C is an internal support location. So from the first equation and from second equation, both are equal to 0, right? And also at this point, the diffraction from first segment should be same as, the rotation from the first segment and the rotation from the second segment should be same at the point C. AO means point C, okay? And at the top end, so y is equal to negative delta, okay? Delta is a positive, this is a negative, so it's equal to negative delta, okay? So here we have introduced, okay, this is a boundary condition, this is a boundary condition, this is a boundary condition, this is a boundary condition. This is a compatibility condition, but in principle we have two compatibility equations. We still have one more. It's a y1 A low is equal to y2 A low. So why I didn't use y1 A low equal to y2 A low? Because we already have a y1 A low equal to 0, y2 equal to 0, so definitely they are the same. So don't need to introduce again. Okay, so don't need to introduce. If you introduce one more equation, okay, you will make complicated. Okay, so please understand, because we have two compatibility equations, but here actually when you introduce these two boundary conditions, you already introduce the first compatibility equation. So this is the reason I just put one compatibility equation. Okay, so please understand. Okay, please understand. And from some equations, very easy to eliminate. For example, you can find A1 is equal to 0, and also you can find delta is equal to B1 times sine alpha A low, right? And from this equation, you can replace delta by A2, B2, and B1. So from this equation, you can replace B1 by delta. So always we are able to reduce the order of the equations. And for example, you can make the final equation only involves three unknowns. You can further reduce. Okay, for example, based on the last equation, you know the relation between A and B, A2 and B2, right? A2 and B2, so you can represent A2 by B2. So in this way, you can further reduce the equation from the 3 by 3 dimension to 2 by 2 dimension. So we're always able to reduce the order of the equations. So this is a final solution. Okay, is a final solution. Okay, we take a 5-10 minutes break and then we go ahead. Okay, and we go ahead. Okay.